Hi, everyone. Our next speaker is Professor Volodymyr Minin. He's a statistician at the University of California, Irvine. He also serves as an associate director of UCI Infectious Disease Science Initiative. His work focuses on using statistics to understand how disease is spread, especially through complex models. He often combines different types of data to improve our ability to predict things like healthcare demand. Beyond infectious diseases, he's also interested in areas like phylogenetics, population genetics, system biology. Please join me in welcoming Professor Minin.
Thank you. Thank you for the invitation. It's so great to be here and a fun day so far. So, as the title says, I'm going to talk about the wastewater with you, and I just wanted to get something clear in the very, I'm trying to be clever here. The signal is not flushed away and so on. I wish it was my joke. It actually, if you know, maybe some of you know, there's a Stanford anthropologist, Jamie Jones, who works in infectious diseases. So I worked with him a little bit, and that's his, so he kind of joked around with me on Zoom about this, and I said, I'm definitely going to use it as a title for the paper and for the talk and everything. So he knows that I'm using it, but it's his idea. So you've heard this here first. So let's begin by kind of just remembering, and for this audience I don't have to say too much about this, but just to remind you the difficulties we all had while analyzing different COVID waves during the pandemic. And when I was doing it, and maybe you had a different experience, when I was doing it, I had trouble when was thinking about mathematical models of, in this case, SARS-CoV-2 transmission, how to think about susceptibility. Because, all of the models that we use have to assume something, like at time 0, I had 80% susceptible population, 90 or 100% or whatever. And it actually was easy in the beginning of the pandemic because everyone's susceptible. When we start, if you want to restart your model before the Omicron wave, because all your models broke, as they did for everyone before Omicron, you had to assume something about susceptibility, like how many people are susceptible right now. And dynamics changes dramatically depending on that assumption. And so, of course, if we have a seroprevalence study, maybe we can rescue ourselves, but they're incredibly expensive. To give you an example, if you haven't thought about the cost, we did the seroprevalence study at UCI together with the Orange County Healthcare Department, and it was very rigorously done, very well done, in terms of representation and random sample from Orange County and so on. It was, let's see, it was $500,000 just to do one snapshot of Orange County, one county population of susceptibility. And so you cannot do it very frequently. So after having these difficulties, I started thinking about, okay, can we have the methods that do not assume too much? So it's sort of like some compromise. I still want a mechanistic model of some sort, but I don't want to be assuming too much about susceptibility. And of course, we're not the first one to think about that. We will start with this very simple task. So this is the graphic from the CDC. I think it's the CFA graphics, Center for Forecasting Analytics, explainer in one of the blog posts. We'll start with a very simple, not very ambitious modeling exercise and statistical exercise of trying to estimate effective reproduction number, which is, of course, just number of secondary infections. And so, which accounts already for the fact that someone may be not susceptible, right? We're not talking about basic reproduction number where we assume that it's a completely susceptible population. We're assuming that we're somewhere in the middle where some people are already susceptible, some people are not susceptible, and so have immunity. Useful summary, less than 1 good, above 1 is bad. That's my scientific explanation of what, how we use effective reproduction number. Ideally, we would like to do it in real time, right? So that's what people call nowcasting, and we want to do it in real time to improve situational awareness so people know, should we panic or not? RT is above 1, let's panic a little bit and think about hospital capacity and other things that we need to do. Traditionally, we do this, and you have seen this, of course, in this group. You're experts, many of you are experts in this. You do it through cases. You take case data, the time series, and you fit some model. I'm going to talk about what people do typically in this case in a second. But cases are problematic because case ascertainment bias can change over time, right? So the reporting rate basically is changing over time, and that's a big problem. For example, it was a huge problem, and if you forgot, I'll just remind you for a second. In the beginning of the pandemic, there were very few tests available, right? And so we were not testing a lot. Then in the summer 2020, we opened this huge testing sites at like stadiums or school parking lots and so on, and then we started ascertaining lots of cases. And the cases increased not because the infections necessarily increased, although they probably also did increase, but it was a confounder, right? Like we were testing more and there were more cases, but it was not an indication that we had huge increase in incidence, right? So these problems are actually hard to deal with, and it's hard to tease it out sometimes. It's possible with additional data, with data integration, but it's not easy. And so that's where the wastewater comes in as a better data source, potentially at least, because when we get some infection, in this case I'm going to talk about SARS-CoV-2 pathogen, but it works also for flu and RSV and mpox. As you can see in the bottom line, I'm saying that that's what the National Wastewater Surveillance tracks these pathogens. But everyone sheds viral RNA into the wastewater. So we're not really only ascertaining some people. So we're not really relying on self-reporting or people going and testing. We are just kind of observing everyone. And you can think about wastewater as just basically an extreme way of pool testing, right? It's a pooled testing where I go to the water treatment plant with a bucket. I take a bucket of wastewater. It has RNA from all the people who are right now infectious at different stages. I do qPCR, and I count how many RNA molecules I have. My count becomes a number. It's a very high count usually. That's why we usually log transform it for modeling purposes. And that's my indication of what's happening. But it may be noisy, it may be problematic, but I don't think it should change over time too much. That basically the scaling factor that transforms number of infections into the wastewater RNA count, that factor is probably constant across the time unless you have huge population movements and like people migrate suddenly in masses and so on. But in a large population, that should be pretty stable. Any questions? I was hoping to throw something, but it's sort of like hedge box in someone, but okay. Oh, hold on a second. Okay. This is just for this visit is worth it. Like absolutely, this is just the best time I ever had at the seminar. Like.
Okay, it's not like a great question, but my question is just is there any heterogeneity in how much shedding per virus strain? Like, is there any concern about selecting for strains that are better at shedding through the GI tract?
That's a good point. So I mean, the honest answer I can give you, I don't know exactly the details. We need to do more of the shedding studies, individual level shedding studies, definitely, and we're not doing that enough, to be honest. I think there's a possibility, but right now, like for the purpose of this academic exercise, let's think about that we're not in the transitional phase where some variant replaces another variant with possibility that this variant may have different shedding profiles and so on. But it's a good point. It still may be another, maybe its symptoms are changing, and maybe this new variant, I don't know, causes more diarrhea, for example, and that changes the amount of RNA that people have. So it is not completely without problems, but I think they are kind of slightly easier problems to think about than the human behavior, for example, and other things that we typically have in cases. But yeah, it's a good point. It's not completely free of problems. I don't want to oversell it necessarily. Okay, so how people typically do this very simple exercise of RT estimation or nowcasting. So the prevalent method is based on the branching processes. So we kind of approximate the transmission dynamics. Let's see what does it work? Oh, yeah. With transmission dynamics with a branching process where each infection produces secondary infections, and we think of them as kind of the particles in the branching process situation. And then what we would like to do, and we can think about this branching process and recover RT from that. I'm going to give you a little more details in a second. But another way, that is not very much used, is you can fit an SEIR model or something like that, a better model, a good, pretty with all the bells and whistles, and estimate RT from your cases or wastewater this way too. But of course, that would be problematic because you would need this S compartment, which I said is actually hard to model, right? Especially at time zero. You need to start it somewhere, and depending where you start will change your result, and it's not identifiable. You cannot have as zero, as a parameter identifiable, unless you have a zero prevalence study somewhere, maybe not at time zero, but somewhere at least in your time domain. So typically we're not doing it this way, and we justifiably so. And I think that's the right thing to do, that we're not doing it this way. But bear with me. I will try to convince you that you can do something with that too. And so current methods, case-based methods, of course, you're familiar with epi-estim, which is the oldest, which is based on this idea. All of these methods are based on this renewal equation idea, which is a branching process approximation of SEIR, it turns out. People mathematically only recently started to understand it. I don't think we fully understand it, but there are a couple of good papers coming from multiple groups that basically try to understand what... It's a very intuitive equation, but no one really knew for many years why mathematically it actually works, to be honest. And only now we starting using really complex mathematics, which I don't fully understand, but I'm trying. We're starting to understand why this is, how you can align it with our typical way of thinking about transmission dynamics in terms of these comparative mental models and other things like that. But nonetheless, epi-estim uses this equation. Epi-estim, I think it's an important contribution, but I hope people stop using epi-estim forever, to be honest, because it's based. It's not. I don't typically, try to be critical of this different software, but it's just too old. In the sense that it uses assumptions that already we know are not working. For example, it uses a Poisson likelihood. If you look at case count, you will see huge overdispersion. You will never see Poisson distribution. It's just, and it completely destroys everything about it. All the good things that are inside epi-estim are destroyed by this Poisson assumption, for example. And that's why when you typically use epi-estim, you will see this, noisy RT trajectories, which make no epidemiological sense. So since then, people try to rescue this, and these methods deal with it better. They assume they do better smoothing techniques. They use negative binomial instead of Poisson. So you can do better, and people have done better. Okay, so and then you need to provide a generation time to all these methods because you cannot identify it from cases. What people did with the wastewater, the first effort that I know of, basically took wastewater, did some heuristic of converting wastewater to cases, and then applied epi-estim to this, which turns out was not working very well. I'm going to show you, and it's not surprising, but it's the first effort, and that's fine. There are other methods that are available. They're not yet, there's no papers that I can find yet with this method. Epi-sewer comes from the same group. I think it's both from Tanja Stedler's group in Switzerland. And epi-sewer is doing something much better. We're still testing it, so I'm not going to show you the result of epi-sewer yet. Basically there's something in the works, but it's fairly new. We don't have a lot of benchmarks yet. Any questions? I promise I will stop throwing this cube at you. I just want to know if you have questions. At this point, I'm interested in the questions, not in throwing the cube. Although it would be kind of fun too. So let's go to my kind of sort of thought that I left unanswered so far question. So if you start with simple SEIR, right? This is as simple as it gets. This is your textbook, little page from a textbook about how to model transmission dynamics using SEIR. And we remember that R0 in this case, you can, if you make your transmission rate time variable, you can also make R0 time variable, so to speak. And then RT will be just R0 multiplied by the fraction of the susceptibles, right? So that's our textbook definition of effective reproduction number. And that's how you could do it, right? You could fit this model to case data, and if you're brave enough and not worried about the S compartment and other things, it will work, so to speak. And if you have a knowledge about susceptibility, it will work. You can do it. You don't have to use epi-estim or epi-now2 or anything else. This will be okay. It's just another way of doing it. It's not prohibitive, as far as I know. Now, as I mentioned, this is hard because, right, in reality, we have SEIRS model. People lose immunity, people vaccinate. So this S compartment fluctuates in this way that you always need to add additional more data, assumptions, make it more complex. So to me, the S compartment was a nightmare during the pandemic when I was trying to work with the California Department of Public Health and do forecasting and nowcasting for them. I was always screwing up because, and every time we would screw up, we would find yeah, we forgot that, to do something with the S compartment or to add vaccination data, whatever, something along those lines. So we're trying not to do it. And so this is it's not going to be very anticlimactic. I'm building, if I'm going to, reveal some, magic. We're going to drop the S compartment. This is a trick. Which sounds kind of stupid when you first think about it, but and people have done it before, but it's not a prevalent way of thinking about it. But if you think about it, you can just say, well, we typically estimate beta T non-parametrically anyway. You typically put some sort of smoothing prior if you're Bayesian, or whatever, anything you want if you're not Bayesian, no, it meant kindly, come on. Wow. I should put aside the shovel and stop digging my grave, right? Okay, moving on. Anywho, so beta T is typically we estimate beta T non-parametrically anyway. So why don't we make a compound parameter and estimate this whole thing non-parametrically? Why does it matter? If I am estimating beta T non-parametrically, that means that I can estimate this whole thing and not worry about separating beta from S. Because I'm saying it's hard, so why not just identify a product of beta times S all the time? They're both functions of T. Their product is a function of T, and I'm going to just doing this non-parametrically. People have done this. So if you look at like this paper 2016 from Theo Kyprianos and Phil O'Neill and their graduate student Shu et al. In 2016, they have done it. People kind of jump on them and said, "Oh, you're not modeling transmission dynamics correctly. You're doing it like this is too phenomenological." And they still published it, and it's there, but it's a second model, as a second choice. But you can do it, and also Tanya Stedler has been doing it forever in the phylogenetics context. When they do their birth death sky line or something, birth death RT estimation based, they basically assume that they can estimate only this, the growth rate of branching process, and that's actually effectively doing exactly the same thing. So it's not a completely radical idea, but what I'm saying basically, I think it's a little more radical, that this is basically equivalent to epi-estim idea, except without renewal equations. So if you do this defines how, if you put the likelihood on it, the model that connects this latent variables to data, you can either do the branching process or you can use EIR. And here, in this case, we're using R1 and R2. Typically for cases, I would just use R. I'm doing R1 and R2 because we know that people from shedding studies, we know that if, at least for SARS-CoV-2, people shed virus after they stop being infectious. So typically, the infectious people period for COVID, we don't think it's more than 5-7 days, but people shed at 30 days RNA. So we know that they shed after they're in our compartment. That's why we decided, okay, we need to add our 2 compartment, which will be recovered but not shedding. This is recovered, removed, but still shedding. What's nice about it, notice this system is linear, so it's actually, you can closed form solution is available. You don't need ODE solvers or anything like that. You can plug it into any software without, we have all the formulas in the paper, in the appendix. You can just type on the formulas, so it's very easy. So it's not as complicated. It's as easy as epi-estim type of idea, renewal equations idea. And you can use it either for cases or for wastewater. So for the wastewater, for example, after I have this ODE, I would just say log RNA counts from wastewater will be generalized T distribution, where my mean of the T distribution will be a mixture, like it's a weighted sum of people in the I compartment and people in this R1 compartment. And so this basically tells me, oh, okay, like maybe it's 50-50, like maybe people shed as much from I compartment as they shed from R1, or they would be, and we will estimate it lambda from the data. Notice I'm making this a little more complex when you think about it. Like, hold on a second, you didn't tell us anything about Tij, whatever, all these indices. So T is just time when we sample. J is a replicate number. I'm not sure, how many of you knew before this talk that when people do wastewater, they do always routinely technical replicates? You don't know about this because it's in no databases exists. No one tells you about this. I found out by accident because I worked with an environmental engineer who does this for a living and was doing it before it was cool, before the pandemic. Her job was to do wastewater sampling of pathogens before the pandemic. So she was doing it for decades as an engineer, like developing water samplers, automatic water samplers that do all of that. And so she gave me her data, and it had 3 observations per time point. And I was like, Sunny, what is this? And she's like, well, we always do technical replicates. We always do qPCR 3 times. And what's reported is always an average. So I went to CDPH and asked them, why are you reporting the average? I want raw data, and I'm still waiting. The modeling team said, yes, we understand why, and we'll talk out to our data science team so they can provide in the California Open Data Portal, where I usually pull the data from. They will give you 3 columns per time point. And I said, like, I'm still waiting. I don't know why. But we have some influential people here that may whisper to someone to report raw data, and I would encourage you, because I'm going to show you that you can squeeze more signal out of it. So I don't know why people leaving on the table data and just report the mean without even standard deviation. No one reports standard deviation of that mean either. Sometimes when people are rich, when Stanford was doing their wastewater, they did 10 replicates in one study. That was very cool, but that's expensive. I'm not hoping for 10, but give me at least 3 or 5, and I'll be very happy statistician. Anyway, so that's how we connect ODEs to data, right? Very simple. Just by the way, t-distribution is here because sometimes there are outliers. I would put normal. As a matter of fact, we did start with normal, but then sometimes these strange things happen. For example, in the wastewater, when storms comes in, it kind of destroys stuff because the wastewater becomes like flooded with some other water, and you have less RNA counts because of that. You'll see in the data. I'll show you in a second how it looks. Yeah, it's in some sense it's similar. Yeah, so it's similar. It's not as bad because normal at least have mean is not connected to variance. Poisson has that variance is equal to the mean always, and if it's not, your data are wrong. And that's why it's a huge model specification that has huge effects on everything. At least with the normal, it's basically you still have variance separate from the mean, but it will be normal tails are too heavy because it will look strange in the likelihood if something shows up in the tail. For the t-distribution, it will look more okay, basically. That's the idea.
One more question on time.
Oh, yeah. Of course, yeah.
I can see that the PIR model really... Oh, that wasn't sure. Okay. That the model really depends on the assumption of viral shedding. Would it be possible to consider the treatment or vaccination in the model as the application can affect the shedding durations?
So if the data are available about the population level, I think it would be possible. But I'm kind of assuming here that I'm not very rich in data in some sense, and I don't know anything about the population. If you know something about the population, you could definitely put covariates here in this model and adjust for the fact that maybe at some time point some treatment was administered and that resulted in less shedding. I think it's possible. We haven't tried it because we didn't really have covariates like that, time-varying covariates. But if you have a good time-varying covariate, it's a good idea to put it in, and it's possible. It's a good question. Yeah, good thought. Thank you. Okay, here's the kind of just busy with notation, but this is just a slide. You don't have to kind of process everything necessarily, but this is all my parameters. I just want to always to be clear about my parameters, like what they are and how many of them there are. So I have all these rates of going like latent period, length of the infectious period, length of latent period, the typical ones. Those are these guys. I have these, t-distribution parameters, tau and degrees of freedom. I have my initial, again, the initial condition problem did not go completely away. I still need to specify how many people I have in this compartment. So that's still going to be a problem. But at least I don't have to worry about susceptibles here. And the R will be, this is a parameter that they basically, we're going to parameterize the RT curve as piecewise constant, as basically everyone is doing. And then we're going to put a smoothing prior on it, random walk prior. And so this is my prior on RT. This is my likelihood, which is just a T distribution-based likelihood, which depends on my solution of the ODE. And I'm going to turn the Bayesian crank. And if I have a likelihood, I have posteriors. I can compute, priors, likelihood and priors, and I have my posterior on the left. It's pretty high dimensional. So for example, it's not too high dimensional, but the number of parameters is not small. It's not 5. It's like, because there are many R's. For each time point, there's a separate R. So it could be 45. It depends on the length of your time series. It could be 450 if you're really analyzing lots of years of data. And that's not a problem because we make this works pretty well even when you increase number of parameters. because of regularization that we're doing. And if you're curious, I'm going to go into the details later about this. Any question? Yeah.
Do you want to throw it to me?
Oh, yeah. Thank you.
I'm now a little confused. I thought R was what you were trying to estimate.
Yes.
So you said there's all these R's and they're so you're treating the thing you're estimating as further parameters.
Right. So yeah. So these are parameters. Theta are kind of my nuisance parameters. All of these I don't really care about, but I need to estimate them. R is my target parameter vector.
Yeah.
That's what I want. This is going to be my trajectory of RT.
You're trying to
That parameterizes that. And yeah, so I want posterior of R and theta, but I don't really care about theta. But sometimes it's useful for diagnostics. If something goes wrong, I still look at theta. Right. Thank you. Yeah. Here. Yes, I'm going to keep it. Aha. Did I jump already? No, I jumped backward. Okay. Any other questions about this? So this is kind of having the ODE and the T distribution assumption. We have kind of almost automatically in the priors our posterior. You can actually do the same. I'm not going to spend too much time with this, but you can do the same with cases. So it's not wastewater specific, this model, right? I can come up with this EIR model. In this case, I don't have to worry about 2 R compartments and have cumulative incidence and then do the usual, subtraction of the subsequent cumulative incidence. This gives you the actual incidence of cases. And you can use the standard negative binomial on cases, and you can do all of this that I just described with cases instead of wastewater. Everything works exactly the same way. And this model would be absolutely equivalent to epi-estim in some sense. I mean, not exactly the same, but they are very similar in terms of what assumptions you need, what kind of... but to me, I kind of like this better because I understand where this is coming from. Like, I understand the parameters better than epi-estim parameters. So I'm not holding my breath for people switching from renewal equations to this necessarily. But it's possible to do that. If someone wanted to switch and do RT estimation only using this framework, it is there. It exists. And it's implemented in the R package too, together with the wastewater. Okay, let's do the simulation. So simulation setup, what we're going to do, we're going to simulate the data in a way that is complex. So it's not a simulation where we're trying to catch bugs in our code. It's a simulation which stress tests our model. Right? There are 2 types of simulation. One, the simulation where you simulate from the model you're fitting. And that's only good for catching bugs. You're not going to learn anything scientifically useful from it. But you still need to do that. But if you're simulating from the model that is more complex than the model you're fitting, that's a real test. That's a stress test. And that's what needs to be done for all new statistical methods, because we never know that assumptions we made are correct. So we're going to use a basically agent-based model where we... I'm not showing this shedding profile. Okay. I dropped that slide because it was too many. But what we do basically, each individual, we have individual-based SEIR, not compartmental, because each individual will shed differently, and they will shed differently depending on at what time point after infection they shed. So for example, if it's 5 days after infection, they will shed less. If it's 2 days after infection, they will shed more. And that data comes from the shedding profile studies. So we grab the data. It's actually, someone has done nice meta-analysis of this data. So we grabbed it from the meta-analysis paper. And we have this shedding profile. And we basically, because our model assumes that it doesn't really matter at which time point in infectious period you are, you're going to contribute the same amount of RNA copies, which is not true in practice. So we're simulating in such a way to stress test this. And this is just kind of what happened in terms of, this is my compartments, and this is actually stochastic compartments. It's just the size of the population is pretty large, so you don't see a lot of stochasticity. But this is a stochastic SEIR, not deterministic one. We fixed this kind of weird RT curve artificially, just to have the true RT curve in place. And this is how the wastewater will look like, and this is how case data will look like. Questions about the simulation setup? So it's individual based, and therefore we can do more, and something I cannot do when we fit the model. Because always, coming up with the models to simulate, it's easier in some sense because simulation is computational and conceptually is easier task than inference. Okay, so now we will have a battle. I was teaching this. I also need to do attribution here. So I taught when I was working at the University of Washington. I was teaching a class for many years kind of how to do research for stat and biostat PhD students. And we were doing it jointly with biostat department. So my partner was always be from biostat. And one year it was Ken Rice, which I don't know if you know him. He's a great guy. He works in statistical genetics, so it's not infectious diseases. And he was teaching how to give a talk, and basically was saying every talk is a story. It's a storytelling exercise, and every story needs to have tension and a battle, and heroes and villains. So here they are. So this is our EI. Actually, hold on a second. That's a typo. It should be EIRR, not two I's. There are two R's. Sorry about that. I didn't notice that. And this is our model for cases. So our main champion, it will be the princess. I like her better. This guy, I don't care for him too much, but he's a hero technically. The Huysman method, will be Prince Humperdinck. But he has a helper. Oops. The Epiestim, so that's his assistant. These guys are not. They're kind of not villains. Remember, if you have S model in your S compartment in your model, you can still fit these models to the data. But I'm saying this will be probably hard because we don't know much about S compartment and so on. But I would say, so Physic and Iñigo Montoya, they are villains, but they're more like victims of the circumstances. They are not really real villains. And the branching process methods, for me in these cases, I'm not saying it's going to be a real villain here, right? Like Vicini will be a real hero. Villain. Okay, you got our champions, like heroes and villains, right? Lots of them. Okay, so let's see what happens. So just very simple. First, let's simulate it once, which is not terribly interesting or definitive, but it's illustrative. So TOPRO is wastewater. So here I have only this is our hero, the dropping S compartment model, EIRR wastewater, and this is our kind of villain, but not a real one. It's the one that if we had S perfectly, and in this case we're very kind to it. So we're not trying to break it. In this case, we're simulating in such a way that we know how many susceptibles there are. So we're not trying to break it. I'm actually trying to see how much information I'm losing by dropping the S compartment. And notice what happens. They look pretty similar, but the S compartment still kind of messes up, interestingly, because it's broken because of individual level simulations. So it turns out the individual level shedding, the fact that it's heterogeneous it's not constant across time, it breaks the S compartment model, but does not break our model too much. Again, here's a little bit, but you'll see it's actually more of a fluke when I do it multiple times. And for cases, of course, for cases it's perfect because I'm not doing anything with cases. It's actually SEIR is exactly the model I use to simulate the data from because I don't have this heterogeneous shedding and anything like that. So it actually works really well, and you have just more uncertainty. If you drop the S compartment, your RT inference becomes better. Oh, by the way, red is truth, and everything else is our Bayesian inference. Black line is the posterior median, and these blue shaded areas are different levels of credible intervals, 50, 80, and 95%. So that was interesting by itself because, to be honest, I didn't realize that how much this would break it, the S compartment, because we're not trying to break it in a way of misspecifying the S compartment. It's actually just breaking because of time inhomogeneous shedding across time during the infectious period. So to me it was interesting that this broke, but this didn't as much. So that's another reason to love this idea of dropping the S compartment, no matter how silly it sounds. Let's do infectious disease modeling, but just let's drop the S compartment. If there's one thing you remember, actually, I want it to be this: the dropping the S compartment is not necessarily a bad idea. This and Jamie Jones' joke about not flushing the signal away. Two things. Okay, let's do it multiple times. So if we do it multiple times, repeat the simulation, we can measure frequentist properties of Bayesian estimation. So, if you're pure Bayesian, you may actually object to this idea because you can say, I don't care about frequentist properties, but I'm not a real Bayesian or not religious one, actually. And so to me, it's interesting to think about, okay, I did the Bayesian procedure. What are the frequentist properties? If I repeat it multiple times, what happens, right? And so here's my deviation, which is a measure of bias. And you can see that the cases give you less bias, but not by a lot. But if the S compartment model, the SEIR model, that gives you pretty significant bias. This mean credible interval width That basically is a matter of precision, like how wide my credible intervals are. If they're narrow, I'm precise. If they're wide, I'm not precise. And so you can see that we're losing quite a bit of information from going from cases to the wastewater. So the wastewater is noisier, and that's actually what I wanted to see, because I knew it was noisier. So I wanted to see this behavior. That kind of means that we're doing something right, that wastewater is the noisiest data, and that's why we should see more uncertainty, which I want, because I don't want to be false advertising something. I want honest representation of uncertainty I have in my data. So interestingly, the S compartment even more uncertain, which surprised us a little bit, but it's because of model misspecification. This one is not particularly interesting. I'm going to drop it. It's just a measure of how true we are to the true curve. It measures total variation norm in the functional space, but I think I'll skip that. That's okay. So you can ignore that part for now. Any questions about this? So, yeah, I forgot the credibility. Sorry, the calibration. So the envelope basically is, yeah, I saw the question. The envelope is, if I count how many times across time points, what fraction of time points were covered by my 80%, let's say, credible interval. This is for each simulation. I will have a number. For example, in one simulation it will be 75%. In one simulation it will be 90%. And then these box plots represent this variation across simulations. And you can see that these models are pretty well calibrated. This is a little conservative. But this is really bad. Like this SEIR model, where you don't drop S compartment, is really miscalibrated. So the 80% credible intervals cover the truth only like 40 or 50%, 40-something percent of the time. So that's not good. But again, it's misspecified, so it's not terribly surprising. But it's very parametric. It's specified and very parametric. When you drop S compartment, it becomes more non-parametric, right? Because I'm estimating it's alpha t, the compound parameter, not parametrically, so it's more flexible. That's why it can still recover in terms of calibration and everything else. Now, number of replicates. This is kind of a boring plot, but I really want to hammer this point down. You can do a couple of things. You can simulate with 3 replicates, 1 replicate, 10 replicates, and then you can say, screw those replicates, I'm going to do the mean. If I have 3, I'm going to take average. If I take 3, I take average, right? So we did these things just to try to understand how much this matters. And I'm going to draw your attention probably, so in terms of deviation, not as much. So because remember, replicates, it's more about precision, more about squeezing more juice out of your data, and less about bias. So bias should be okay, but look at the precision. So here's my, of course, if you do 2 replicates, you have high precision, really small credible intervals. That makes sense. But you notice if you take the mean of 10 replicates, you're here. So you can do much better. Even for 3, look, this is 3. If you're just taking the mean, this is your precision, and you can drop it if you use raw data, because you now can estimate technical noise and kind of decouple technical noise from environmental noise in some sense. So this is using raw data, just 3 points, instead of the average of these 3 points at every time point. So that's why I'm a little mad that I don't have access to the raw data, because I could squeeze a little more. I mean, if you think about it, maybe it's not huge. I don't say it's like going to be groundbreaking, because look, so typical credible interval would be, let's say our RT is about 1. My typical credible interval would be 0.4 maybe, like plus minus 0.2 or something like that. That's kind of okay. And that's what we're seeing here. It's like 0.36, the mean credible interval width. And you can go from 0.36 to 0.3, I don't know, 4, 3. So it's, it is like second decimal place. It's not huge. But why throw it away? I still don't understand it. Like, even if it's small, why throw it away? Like, I still want to use it. And it actually could make a difference, because if your credible interval contains 1, you would not raise an alarm, and it's possible that it will not. Maybe you can detect outbreak earlier by 1 week if you're using this method, even though it's a small contribution. And so that's still, again, if you use more replicates, you'll get more bang for your buck for sure. But people don't use more than 2 or 3, to be honest. That's the typical setup. This is comparison to Huysman method, and we tried to make it as much to make it work as much as we could, but it's basically not working, at least in our simulation. Maybe our simulation is too harsh for the method, but it's not calibrated, and it just has these weird outliers a lot of times. So I would just say in this current form, it's not working, but hopefully help is on the way using this episewer and other methods. But at least Huisman method that is just converting wastewater to incidence data, it's not working right now, at least not in this simulation. A little case study. So this is the Sunny James data where I have raw data. I have not just means, I have replicates actually. And so this is from the LA treatment plant. This is roughly delta Omicron. So this is delta wave, this is Omicron wave. And those are cases, and this is corresponding wastewater. Here I'm actually plotting at each time points 3 points, 3 replicates, and I'm the solid line is just mean going through them. Occasionally there would be a point here, for example, where it's just 1. It's possible that they just lost, they tried to do 3 replicates, but PCR failed 2 times. And that's the main reason they do replicates, because they know that PCR fails. And so they don't want to do it once, because if they do it once, this day was not covered, like that's it, or this week. So that's why they do 3, just because they know out of 3, it's unlikely all 3 will fail. So sometimes we have 3, sometimes we have 2, sometimes we have 1. But most of the time we have 3 replicates. And this is the results. So again, just to illustrate this point, the Huisman method, in my mind, produces something epidemiologically not plausible. Right? RT is jumping up and down all the time. But it's pretty typical for epiestim behavior too. Like epiestim also sometimes does it, like jumps around with narrow credible intervals. So it's part of it epiestim, part of it is the way they transform wastewater to cases, I assume, which I don't fully understand how they do it. Well, I know how they do it, but I don't fully understand why it's good. So I think that's not, I mean, you can see the real peak of RT in Omicron, but lots of false positives basically in terms of RT going above 1. This is us doing cases, case data. This is us using wastewater. Notice there's some disagreements. There are multiple small ones. First of all, this peak is higher. And also there's bump. All the methods we tried epiestim, epinow2, epidemia. There's always this bump appears right here, which I don't see anywhere in the wastewater. And it's probably something to do with reporting rate. We don't know what it is. We didn't find it in hospitalization data. The bump does not exist. So it doesn't exist in any data, but in cases you see some bump in RT that bumps RT a little bit above 1 for some reason. Actually this is between Delta, this is October 2021, so it's between Delta and Omicron. Omicron has not arrived, but Delta already finished. So, and I think it's an artifact of some reporting probability. Okay, I want to tell you 2 projects in progress. So this is work has been done, and I provided the reference, I think, for the paper. Just briefly, what we're working right now, there are 2 extensions that we're working on, which are both actually quite, not complete, but very close to being complete. One is the stochastic model for small populations. So it turns out, if I want to put an autosampler, water autosampler at a hospital or dorm on campus or a correctional facility, and I want to monitor a small population, let's say 1,000 people, using differential equations is not a good idea because you have a stochastic behavior of the in small populations. And so it turns out you can convert it if you, of course, analog of, no, not analog, but extension of ODE would be this very simple Markov chain with these compartments, for example. I mean, if I drop R2, I just kept 1. And actually, it's analytically solvable. The variance and the mean, covariance and the covariance and the mean is analytically solvable. And you can kind of do the same thing as we did, except you have one more term. So this is the term which models latent H compartment. In this case, H is your exposed and infectious individuals. And you can actually compute this. It's very easy to compute, and we show it in the paper using normal approximation. And that says that these trajectories are stochastic, right? Before they were deterministic, that's why this term was absent. There was no probability associated with the latent E and I compartments. Now there's a probability term associated with E and I compartment. And that's actually important. I'm going to show you why in a second. If we do the same simulation, not the same, but kind of similar simulation that I showed you, but in small population. Before, the simulation I showed was in a population of 100,000 people. So it's kind of county level simulation. This is 1,000 people. So this is the wastewater for 2 different trajectories. One that starts at 2 and drops, one that goes up and down. And this is deterministic model, and this is stochastic model. And notice they're very different. If you look at this, like for example, like this deterministic model entirely missed this trajectory here. This also struggled a bit, but it captured much better. And so we have multiple simulations showing that stochasticity here really matters. Like in a population of 1,000, if you're modeling a dorm or a hospital, using ODEs will mess with your model quite a bit, not in a good way. And then the second extension we're working in, we're hooking it up to hospitalization data. So if you extend this model, again, it's the same model without S, but now I have the H compartment, which my hospital compartment then removed. You can now jointly analyze wastewater and hospitalization data and do nowcasting and forecasting jointly, nowcasting of RT and forecasting of hospitalizations. One problem I want to disclose is that I forgot to mention, which is a kind of a big thing. So these models are very simple, right? They are not real. They're very crude approximation of reality that we're using. RT, I showed you that we can estimate very well, pretty well. What I didn't show you that if you look at estimation of the I compartment, I trajectory, it's not working. Like it's biased, it's severely biased. Like the I compartment, actually, we are misspecifying all the time. So when we moved to hospitalization, I was like, okay, hold on a second. But in order to predict hospitalized people, I need to have a pretty good idea what the prevalence is in the population. So if I'm screwing up I compartment, I'm going to screw up H compartment. And as a result, everything in my forecasting will be screwed up. So that's why we knew that we had to introduce this time-varying hospitalization probability, which is not real. Even if hospitalization probability is constant, I still need that to correct my screwing up with the I compartments thing. So it's a hack. It's not it's not an elegant mathematical model. It's really a hack, a statistical hack for me to fix the problem with the I compartment that I'm having. Yeah. Hold on a second. Hold your horses.
Is the mess with the I compartment because the distribution of infection is not exponential?
No, the messing with the I compartment is the result of the fact that we are assuming that no matter where you are in the infectious period, you shed the same. That's the biggest problem, which is really hard to actually fix in a way that is tractable computationally. It's very easy to fix mathematically. Like I know how to write the model. I don't know how to do inference with that model. But it's the fact that in reality, shedding profile is like on day 1 you shed a lot, day 2 even more, and then it drops quite significantly and goes out to day 30. And so that's something that is very hard to model in these compartmental models. We actually did this. You can introduce lots of I compartments, each assuming different shedding, but it becomes kind of a mess and it's not fully identifiable. So, but we did this in the second paper, played with that idea. But that's the major reason. That's the biggest model misspecification that is interesting to solve. And so here's an example of. Sorry, did you show me the time already or no? Okay, yeah, good. I just want to make sure that I didn't miss it. So this is an example of. It's actually pretty recent. It's like ending this summer, 2024. And this is 3 counties. Sorry, these counts are low because I forgot to expand the range here. This is San Francisco County. It's much smaller than San Diego and Orange. Orange County is my county. It's 3.2 million people. San Diego, it's 3.4 million people. And San Francisco, I don't remember, but they're much smaller. We don't think too much about Northern California and Southern California, so I don't remember the size. No, sorry, I just don't remember all the sizes. It's Northern California people that usually are snobby about us. They think we're not smart. So no, that's what they think. That's what they tell us, like in our face, actually, all the time. I don't know why. And so this is the wastewater corresponding to that. And what we're trying to do, we're going to try to do forecasting. So we're doing some. I don't have time to explain it. I didn't want to explain it, but we do some interesting kind of hacks here, and then we evaluate our forecasting. So this is going to be our forecasting window evaluation. So here we're going to forecast hospitalization in 3 counties using both data streams, hospitalization and wastewater. And we're going to have 2 models. One that uses just hospitalization, which is kind of what you would do normally without any wastewater. And then this is hospitalization with wastewater. And I'm going to show you a couple of examples. For example, if you look at this is an interesting case study. So here we're talking about San Diego County. And notice how much overshoots the forecast, the 14 days forecast. So each row is a different forecasting horizon, 7 days, 14, and 28. This is the most important probably because I don't actually think we can do it very well at 28. The most you can hope is 14 days, to be honest. Like none of the methods work very well after 14 days that I've seen so far anywhere. But here, notice how it overshoots San Diego County hospitalization. And if you look at this, it actually makes sense. If you look at hospitalization data in San Diego, notice how fast it starts to grow at some point, like really shooting up. Not so much in Orange, not so much in San Francisco, but in San Diego shooting up. But then the wastewater kind of moderates and says, you know what? Wastewater kind of looks like Orange County. It doesn't look very different from Orange County. So wastewater, in this case, kind of moderated. Whatever signal was there in hospitalization data, which was strange, it moderated it. And wastewater said, no, it's actually not as bad. And retrospectively, when we evaluated this forecast, right, the black lines are the real data, and these colored lines are forecasts that were made without looking at this data. Actually, this forecast was made without looking at these 2 data points. It only was looking up to this, right, because it's a 2-week, hold on a second, no. Yeah, looked at this data point and forecasting 2 weeks ahead. And so basically it's kind of a proof of principle that wastewater can be helpful in the forecasting, which people were hoping for a long time. And CDC, CFA people I know working on this, and they have some preliminary results on the blog there, not as a paper yet, but on the blog. So it looks promising that the wastewater can help with hospitalization. I think CDC approach is very different. They took a renewal equation approach, which is, again, a parallel track. I think both are okay, but we're taking this kind of compartmental model without S approach, and we're kind of seeing in some sort similarly promising results. Any questions about this forecasting? I kind of explained it briefly, but I just wanted to draw your attention to just one interesting point. Yeah.
This is the first time we've actually been throwing them. Everybody else is too gentle with them. But so
nice.
You've introduced an important innovation. So I've been sort of watching and occasionally kibitzing on the CFA work. And what I have come to believe is that it's not a question of wastewater helps or doesn't help. It's a question of a particular model has certain properties, and adding wastewater can change those properties. And sometimes if, for example, wastewater tends to increase the forecast, which is not really true, but if it has some very simple effect and the forecasts are typically too low, then that's good. But if the forecasts are already too high, then that's bad. And the CDC work has been showing that, in some points it does a whole lot better with wastewater, in some points it does a whole lot worse. So I think it might be important to not say wastewater helps or doesn't help, but wastewater helps a model or doesn't help that model, because it might be a different result with a different model.
It's true. Yeah, I can see that it's true. Moreover, actually, you can see it even here. For example, there's an interesting example in this 28 forecast. Look, the wastewater actually in this case didn't help. So actually, look at this, right? So this is bad. Both forecasts are bad. They both overshoot. But the wastewater overshoots more than the hospitalization. So you can see it in some cases too. I'm still, this is still in progress. So I don't know. It's something that we don't quite do right with the wastewater. That's my feeling. That it's not quite. We're not yet understanding some of the either outliers or some other things that's happening with the wastewater. So I'm not convinced it's just a modeling problem. I think it's a problem of us maybe like handling the data so far, or not handling, but kind of modeling the noise in the data faithfully. Because to me, if it's not helping, it should just stop doing stuff, right? Like if it's not helpful, step aside. That's what I want wastewater to do. And right now, it's not always doing it. And I think it's kind of my fault as a modeler right now, at least in this case, is that I see I'm probably not making my model flexible enough, so the wastewater does not step aside for some reason when it's not helpful, and it should.
Right, yeah, I think we've been looking at drafts and trying to figure out how to frame, because the results of the CDC model, the initial results were that it made it a lot better, and the final results are more that it sometimes does and sometimes, on average, it's a tiny bit worse on average, but that's a mix of much better and much worse. So I think it's important, like, because people will invest or not invest in wastewater, depending on their very shallow understanding. I think that's why I'm being a little bit pedantic about it. This model, but the fact that it improves one model doesn't mean it will improve the other, and the fact that it makes something else not better or worse So I think so far we don't understand enough to say it's useful or it's not useful. We only know how to say it's useful in a very limited case.
No, I agree.
We need to understand better what those cases are.
Right. Yeah.
Are there like situations where wastewater would be a good thing? For example, in countries that you don't have good case count, or situations that
you mean U.S., right? We don't have good case count
okay,
data.
Yeah, I was thinking like in other countries that.
Okay, I was thinking U.S.
Okay, yeah, that.
Limited resources, you mean U.S.
Yes, exactly. Yeah.
So situations where you can say for sure if like the count of cases is this way, wastewater is like definitely good, and some others that might not be.
Yeah, absolutely. No, it's a pretty cost-effective way of doing it. Of course, it's a pooled sampling. Pooled sampling. The whole idea of pooled sampling was always to decrease the cost, and wastewater is extreme case of pooled sampling, really. Pooled testing. Sorry, pooled testing. That's what I meant. In some sense, it's not called that, but it is what it is, like physically, basically. Okay, with that I will end with thanking my collaborators. So most of the work I showed was done by Isaac Goldstein, who was a PhD student and now is a postdoc at Stanford. The forecasting work is actually right now is done by current PhD student Christian Bernal Zelaya, also a PhD student in UCI. And Daniel Parker is a public health epidemiologist. Sunny Jeng is an environmental engineer who was doing wastewater surveillance, not at scale, but before it was cool. And then Tomas Leon and his team from CDPH are always helping us understand the data and sometimes get data that is not publicly available. So with that, also the paper is published already, not the last two projects, but the main project that I talked about. And there's also some interesting question about spatial dependence of the wastewater signal and better smoothing techniques. There's R package. We actually wrote everything in Julia. So there's a Julia R package, which is a kind of more obscure programming language for scientific computing. But we also wrote an R package wrapper around it. So this is you can get both and play with the software. With that, I'm going to thank you and ask lots of questions.
Thank you. I think we have time for one more question. You have one, or you want to?
Wow, that's a good throw.
Is there any benefit to the nuts implementation in Julia, or is that just because that's what you use?
So it's interesting. We actually moved to Julia. Right now, you can do the same thing with nuts. We don't do it so because Turing in Julia. Turing is a analog of Stan in R. So they implement nuts. So it's the same algorithm. Nuts implemented in Julia package called Turing. It used to be that Stan was much clunkier with solving ODEs back in the day. So that's why actually when we moved to Julia, because Julia is actually amazing at solving ODEs and still beats Stan in terms of speed. So when you want to solve large ODE systems, you cannot beat Julia. It's the differential equation package is amazing. And it works seamlessly with anything else, any inference you want to do, optimization, MCMC, whatever. You just plug it in and it just works. So it's more flexible. But these particular models, it doesn't really matter. Moreover, some of them are analytically solvable. We don't even need numerical solution of ODEs. Some of them we can solve analytically.
Are you using an adaptive ODE solver in Julia?
Well, it depends. We usually play, for any particular model, we play with the ODE solvers for speed versus MCMC, because there's a trade-off.
Yeah.
If you can be sloppier in ODE, but then it will hurt you in MCMC convergence, or you can be very, but it's a speed, it's a balance. So we usually play with the solvers and tolerance to get the optimal MCMC behavior. It's surprisingly connected. There's even paper by Stan people explaining why it's connected.
Does it matter where you're at in the epidemic for that?
Probably it probably does, but we didn't play with the time, where we in time too much. We mostly just played with what type of ODE solver and what tolerance we